Welcome to the Picture Language Seminar. It's November 20th. What is it? November 12th. Here in Cambridge, we're so happy to have Liyuan Chen. He's going to talk about work in a very interesting paper, which is about to be posted on the archive. And we're going to get the title Universal Circumstance with S3 quantum double. Yeah, we're very much looking forward to your talk.
Thank you. Thank you for the introduction. I am Liyuan, an author's PhD student, and this is an upcoming work. This realization of this universal circuit set with an S3 quantum double. So in this title, we have several parts. Like this S3 quantum double is the platform we are using to realize this circuit set. And then we talk about circuit because we want to realize that in current experimental platform. And this circuit set is potentially fault-tolerant. So in the future, we believe this is a protocol that we can build a large-scale quantum computer based on this. Yeah. This is the outline of my today's talk. I will separate our main contribution into 3 parts. Except for this introduction and summary, I will talk about this universal gate set, and I will talk about a circuit, and finally, I will talk about how to do active error correction on this protocol. Okay. Before I go into the details, let me thank all of my collaborators. Yanjie is a PhD student at MIT, and Rui Hua is a postdoc fellow at Berkeley, and also my advisor, Arthur Jeffy. Okay, let's go. So why people believe quantum computer is good? Because it uses this qubit to do computation. Qubit is just superposition of 0 and 1 state. So people believe that because we have much more degrees of freedom compared to only have 0 and 1, we can have some computational power compared to their classical counterparts. And actually, people have shown many different advantages. For example, like Google's quantum supremacy. Then, right now, we are in a noisy intermediate scale error. Like this is called NISQ error. Every device in our quantum circuit will have noise, and this will generate error. So a big problem is that how can we finally realize a fault-tolerant quantum computer that is reliable to do any computation we want? We want to build a practical computer. We want to go from NISQ to fault tolerance. And how can we do that? We are in a classical world. Then, right now, many quantum devices have shown that we can do computation in this NISQ era. Finally, we want to go into the fault tolerance era to cope with all of those noise. There are errors in our quantum circuit. How to do that? We must do quantum error correction. And this is a very wide field, maybe the main field in quantum computation. Yeah. And then to realize this goal, people devise different error correcting codes. For example, this one, the Shor code, is the first one, devised by Shor. And also for those codes, people encode multiple physical qubits into one logical qubit. That if you have some physical error on one qubit, you can check other qubits. You will see, okay, this is still 0. By majority vote, we can correct those errors. This is the basic logic of this error correcting code. And this is one of the examples called Topological or surface code on a two-dimensional plane. They are one of the major examples in this class called topological codes and how to do error correction on this surface code. If we have this two-dimensional plane, and the error will appear as a poly Z string, or maybe poly X string, but here we just talk about this Z error. This Z error happens locally, and then the syndrome detection at both ends of this Z error will tell you we have some Z error at this place. Then we can apply just this Z error, Z operator on this Z error to correct that. So this is the way people do detection and error correction. So finally, we come back to a clean copy of this quantum memory. No error happened. Only when you have a very, very long Z string across the whole copy, you will have a logical error because this error is undetectable. So, but in this case, if we assume this copy has has length d. This will mean that if you assume independent error happen on each qubit, the logical error rate will be suppressed to p to the d over 2 to have this very large Z loop. So by increasing the system size, the logical error, if you have this system perfectly, the logical error will be suppressed exponentially. So this is a typical way to do error correction. Local errors can be detectable and correctable. Only large errors are non-detectable. But the problem is that we want to realize a functional quantum computer. So we need to do universal quantum computation. What's the meaning of that? If you use a quantum circuit to do computation, has qubit input and unitary gates as the computational gates, and also the measurements output, you need to realize any unitary you want. This is called a universal quantum computation. Otherwise, it is not distinction. There is no distinction between quantum computation and classical computation. Yeah, and there is a concept called universal gate set. You can use basic gates to compose this universal gate, and that you can get any large unitary you want. Okay, so if you have this gate set, you can do universal computation. Definitely. One of the example is called Clifford gate plus magic gate. So Clifford gates are this C0 gate, Harman gate, S gate, and magic gate is this T gate. If you think about qubit as a vector, then this T gate is a matrix on these vectors with this pi/8 rotation on this one state. And then you may think that if we have universal quantum computation, and then you do quantum error correction, combine them together, you get a computer. It seems easy, but actually when you want to do things together, you will face a problem called compatibility. Typically, you have one property, you have another property, you cannot combine them together. This is very, very hard. I will give you some example why it is hard. For those topological stepwise codes, this surface code in 2 dimensions, it has been proved that there is no fault-tolerant T gate, just this gate, no fault-tolerant T gate in this topological surface code. So you have to do things called magic state distillation to get high fidelity T gate to suppress the error rate to get a reliable computation. This is not good because it is very expensive. Then the second thing, maybe you can use other codes. For example, the 3D color code. You can realize the universal computation by lattice surgery, and it is fault-tolerant. But the problem is that this is in 3D, 3-dimensional. So you need another extra dimension to do the computation. This is also the extra resource overhead. A conclusion is that extra resources are always necessary if we want to do this QEC plus UQC for this stabilizer codes. So how about we go out this topological stabilizer codes? One option is called topological quantum computation. And this is what I'm working on. People use non-Abelian topological codes. They are also in 2D, so you don't need to worry about this 3rd dimension. And then their excitations are called non-Abelian anyons. So how to use non-Abelian anyons to do computation? This is a picture showing that very vividly. Like if you, the vertical direction is the time direction. And then if you have a copy of this topological code, then you create many pairs of non-Abelian anyons as those green lines and red lines. Then this is some initialization of qubits. And then you do the braiding between those anyons. This is unitary gates. And then you do the fusion, just fuse those anyons together, come back to the vacuum. You measure the total charge of those anyons. And this is like the measurements. People believe that because all of those operations are topological. Topological means that they are on the waterlines of those anyons. People believe that it is fault-tolerant. And then because non-Abelian anyons, they have multiple fusion results. Like alpha is non-Abelian anyon, beta is non-Abelian anyon. And if they are fused together, you will have multiple fusion results, gamma, delta, and whatever. And people believe that this will give us much more computational power compared to the stabilizer code. So this is a logic. People believe that this is one way to realize this UQC plus QEC. Okay, and then there are many experiments recently showing that we actually can realize that in just maybe cold atoms array or superconducting qubits. For example, this one is for D4 quantum double. It's one of this topological order. It has been realized just in maybe last year in this ion traps. And also for this Google, I have a citation here for Google. This is realized the Ising anyon on superconducting qubits. And also recently, there is a group in China showing that Fibonacci topological order, another topological order that can be realized in superconducting qubits. So we have many experiments to support that. Maybe we can build a topological quantum computer that is fault-tolerant and can do universal quantum computation. So we want to explore this direction. Okay, so how can we build this practical topological quantum computer? You want to combine these 3 things together: universal quantum computation, quantum error correction, and experimental feasibility. And as what I said before, this is typically very difficult to combine all of those properties together. Some of the candidates are not good. For example, A5 quantum double model. This A5 is a group, has a group order 60. So it can realize universal quantum computation by just creating the anyons. But the problem is that it requires 60-dimensional local Hilbert space on each edge. It is impossible to be realized by current experiments. Another one is maybe you can think about the Fibonacci topological order. It only requires qubits on each side, 2-dimensional. But the problem is that realizing this one will require you to have very complicated circuit structure. And the gate in the circuit is so complicated so that you cannot make a high fidelity for those gates. And the weight 16 single measurement will reduce the error threshold. These are the problems in these candidates. And maybe there is one optimal solution. It's called quantum double S3. And this is the S3 in our title. Yeah, S3 is the permutation group of 3 elements. So it has group order 6. It can be encoded into qubit and qutrit. And there are many papers have shown that you can use quantum circuits to prepare this S3 quantum double model in experiments, and maybe in constant depths. So it is very surprising. Its preparability is very, very good. And also, its computational power has been shown by other papers that you can do universal quantum computation while braiding anyons and doing measurements. And finally, you can do error correction. This is also shown by other papers. You have an error threshold under certain condition. So it seems that if we can combine these 3 together, you can have an optimal solution to build a good quantum computer. But the problem is that the compatibility always be here. We have many things to do. And in our paper, we have shown that we can do most of the things. And the remaining thing is just one we want to solve in the future. And this is our contribution. So let's go ahead. Like how to do universal quantum computation by this S3 quantum double. The first thing, you need to do encoding. Encoding means what is your logical qubit or logical qubit? The first try is by Muchon. Muchon used local degrees of freedom of non-Abelian anyon to do this encoding. You can see if we have a pair of non-Abelian anyons. So here I should mention that non-Abelian anyons can only be created in pairs. And then if you have a pair of non-Abelian anyons, if you have a local error, the local degrees of freedom will be changed immediately. So there is no any fault tolerance in this kind of encoding. So this is a big problem. And then Cui, Hong, and Wang, they propose another encoding using anyon type. And anyon type is stable under local perturbation. So this is their main motivation to use another encoding to encode their logical qutrit. So let me show you why we have this intuition they are stable under local perturbation. If we have a pair of alpha anyons separated far away, their anyon type is stable under local perturbation. So if we have a local error created a pair of beta anyon, then you can do decoding. You will see, okay, this pair of small anyons, there are some errors generated by noise, such that we can just fuse them together and correct and go back to the original copy. And this alpha anyon, because they are far separated, their logical information is still here. So this is the logic how we can think about this protection. These people have shown that they realize a universal logical gate set by this encoding, doing braided and measurements on these anyon types. So the first question is how to realize it potentially fault-tolerantly. And this is our first contribution. We use this idea like local errors can be corrected. So we want to do every operations remotely. Our first contribution is that we realize all operations in Cui's protocol remotely. We design a specific anyon interferometer to measure the anyon type remotely, and then we also realize the multi-qutrit gate remotely. Okay, then we want to think about how to realize that in real experiment. There are many circuits in the noiseless condition. I should mention that this is noiseless condition. Construct those circuits for this quantum double model. They are realized in qubit and qutrit, and you can prepare ground state and also this single anyon movement operator very easily. But the problem is that if you have noise, things are completely different. If you do quantum error correction, you have to fuse those anyons. That's why I have mentioned it before. You fuse the local anyons, and these circuits are not compatible with those fusion process. And also, when you have fusion, you have to think about how to coherently move those non-Abelian anyons, because fusions will give you different results for these non-Abelian anyons. Then this is our second contribution. We construct circuits also based on qubit and qutrit, also based on their construction, that it is compatible. It can move non-Abelian anyon to control the non-Abelian anyon that is compatible with fusion, and quantum error correction. Yeah, please.
What does remotely mean on the circuit level?
Remotely means that you observe the non-Abelian anyon far separated with each other. And then if you do braiding, you just always keep them far away from each other. And then if you want to measure the charge, typically people can move them closer to fuse the charge, to fuse the anyon and then to measure the charge. But we don't want to do that. We want to still keep them here and measure the charge. I will show that this is called anyon interferometer. Yeah. Good question. Okay, so the last thing is we realize this UQC. We show that it is easily preparable in experiment. The next problem is how to do quantum error correction in this circuit. There are many papers showing that non-Abelian anyon system S3 can do quantum error correction. So the first thing we do is we can map this circuit level noise into anyon errors, and we have proved that the quantum error correction in this anyon model, like in those previous works, is equivalent to quantum error correction to those circuit level noise. So it is in principle can do quantum error correction. But the problem is that those previous studies, based on the assumption that non-Abelian anyons can be moved instantaneously. Namely, when you are moving the non-Abelian anyons, this is perfect. But this is not true, because non-Abelian anyons cannot be moved instantaneously. They have moved step by step by step by step. So this is a conclusion. So we have to consider errors may happen during the movement. And this is a scheme called continuous error correction. Namely, you move the anyon to do error correction, but in this process, maybe error will happen. Yeah. In this case, there is only one paper by these two people, Potter and Wooton, showing that for Ising anyons, the threshold is 10 to the minus 17. Let me explain that. For current device, the error rate is 10 to the minus 3. If you want to go to this extremely low error threshold, it is impossible. You need maybe thousands of years to improve the fidelity. So we must do error correction to suppress the local error rate below this error threshold, such that you can have large-scale quantum computation. And this is our fourth contribution. We find a solution how to suppress the local error rate in our circuit to this possible extremely small error threshold. We design some local error correcting codes to encode every qubit and qutrit in our circuit. And those error correcting code enables all the logical gates in the circuit of this quantum number S3, such that we can suppress the error rate to sufficiently small to satisfy this requirement. So these are the four contributions in our paper. And so that's why we can come back to our outline. In our outline, I separate our contribution into 3 sections. So let's go to the first one, universal quantum computation. How can we do that using this S3 remotely? So I will give a one-page slide to tell you what is quantum number S3. This is important because otherwise we cannot know the operation's meaning. Yeah, and because quantum number S3 is actually a non-Abelian version of this Z2 toric. So I will introduce them in parallel. Toric is in a 2-dimensional plane. On each edge is a qubit, right? And this quantum number S3, actually it is also in a 2-dimensional plane, but on each edge is a qubit. This D is a dimension 6 of this S3 group. And we have group elements on each edge. Then in toric, we detect errors by those star operator and this Plaquet operator to measure those noise. And also in the quantum double S3, we also have this Plaquet operator and this vertex operator defined this way. In the vertex V, we have this AGV as this vertex operator, and in Plaquet P, we have this BP operator. They are very similar to toric's measurement operator. Then by combining them together, you will have this KRCS operator to measure this syndrome. Then you will ask me, what is RC? What is S? S is a pair of vertex and plaquette. You can see here, I choose this plaquette and I choose this northwest vertex to group them together to give you a site. This S is just this pair of vertex and plaquette. For each site, you have this vertex operator and you have this plaquette operator. You smartly combine them together, will give you this K operator. Yeah, this is some detail in the algebra. And then if you want to check that, you will need 2 months to check that. Yeah. So for different sites, this KRC operator commute with each other. This means that you can simultaneously measure all of them together. And this is the syndrome measurement in this quantum double S3. Yeah. The next question is, what is RC? Because it has been shown by Kitai that on each site, this vertex operator and this plaquette operator, they satisfy the algebra of this quantum double, dream field quantum double algebra. such that on each side, the vector space is separated into those irreducible representations of this string field quantum double algebra, and they are just labeled by RC. So you just remember they are just irreducible representation. And in quantum mechanics, we know that irreducible representations are particle. So these are just non-Abelian anyons on each side. So that's the reason why we can have these non-Abelian anyons on each side using this model. If this dimension of this irreducible representation is one-dimensional, we have Abelian anyon. If they have higher dimensional, we have non-Abelian anyon. Because, for example, if you think about group theory, you have high-dimensional representation. They fuse together will give you multiple results, and that's the reason why non-Abelian anyons will have multiple results. Yeah. So far so good. In torical, excitations are generated by string operators. Like you have a Z string, a string of Z Pauli operator, you have a pair of charges at both ends. If you have a string of X operator, you will have magnetic fluxes at both ends. In quantum double model, this is the same. If you have a ribbon operator called FRC rho, RC is the anyon type. Rho is the support of this F operator. You will also have a pair of RC anyon at both ends. So it is completely like one-to-one correspondence between this torical and this quantum double model. And yeah, in this S3 quantum double model, we have 8 types of anyon. 2 of them labeled by A and B are Abelian, and 6 of them, C to H, are non-Abelian anyons. So that's it. The take-home message of this one is just quantum double model is a non-Abelian version of torical. You only need to remember that, and other things you can forget. Okay, so there is a very important concept called anyon configuration picture of this quantum double model. This is by this measurement. I have mentioned that before. This K measurement is the central measurement for this quantum double model. And if you think about that, if you are in a ground state, namely no anyon excitation on this ground state, by performing this K measurement on each side together, I define it as MK, you will get a configuration with all vertex. Vertex correspond to side 1 to 1. All vertex has a trivial type of anyon, A here. This is a configuration of anyon. And then if you create a pair of C anyons on this ground state, by this measurement, you will get a pair of C anyon at the corresponding vertices. This means that there is a one-to-one correspondence between this lattice model of quantum double S3 and the anyon worldlines in anyon theory. So we can only focus on this anyon theory, and then we can just map it back to the lattice model. Then we do this computation. They have one-to-one correspondence. And anyon theory are just described by this category theory. Okay, this is very good. We have a way to go to the anyon theory. Then the first thing is how to manipulate the anyon. Maybe you will think that in this quantum double model, we have this K measurement. We have this ribbon operator. Ribbon operator create a pair of anyon at both ends. So simply we just create a pair of anyon by just applying this ribbon operator. It's good. In the noiseless condition, this is good. But when there is noise, because there is in long-range entanglement in this ribbon operator, it will entangle the first qubit to the last qubit. And this will make the error also propagate from the first qubit to the last qubit out of control. For example, if you have an X error in the first qubit, it will definitely propagate to the whole ribbon when you are applying this ribbon operator. This is a large logical error. If you still remember that a logical error is created by a large loop. So we don't want this to happen. How can we avoid that? We want to only apply shortest ribbon operator with maximally mixed local diffusion freedom. This is some details. I just label it here. And then this shortest ribbon operator, you use that to manipulate anyon by some other methods, by fusion. How to do that? Our goal is to move. If you have a pair of alpha anyon, and then you move the right alpha anyon one side to the right. This is our goal here. How to do that? We want to apply the shortest alpha ribbon operator for this F alpha rho H. Rho H is just horizontal ribbon. And then we perform the measurement intermediately. If the measurement result is just vacuum, we effectively move this alpha anyon one side to the right. This is a basic logic. But the problem is that non-Abelian anyon may have multiple fusion results. If it is not trivial type, they did not fuse to vacuum. How can we correct that? We will not go into the details, but we construct all of the protocols using this similar method to move non-Abelian anyons. And they have this success probability exponentially close to 1. This n is the number of rounds we apply this mk. So we can always use shortest ribbon operator. In this shortest ribbon operator, error will not propagate out of control. We use shortest ribbon operator to move non-Abelian anyons, one side, one side, one side, and then you can ensure the success probability is exponentially close to 1. This is our first contribution. And based on this one, we can do universal computation. Because in Shang-Chui's U model, the universal gate set is composed of 3 things. Before I talk about it, I will introduce what is U model. Otherwise it's too fast. So for this U model, we use 4 D anyon and fuse them into 1 G anyon as our logical qubit. Remember, we encode this logical information in the anyon type. So the intermediate X, Y anyon are the logical information. They are unobservable. This X and Y, they can take many different results. And Shang-Chui, they only take the subspace for this U space, GG, AG, and GA corresponding to X and Y as our computational basis. And the other space, U per, is just this guy. We don't care about it. So they only take this U space, and that's the reason why it is called a U model. You take a subspace to do computation. And how to prepare this logical qubit? It is very simple. In this quantum model, you can create 4 pairs of this D anyon, and then move 1 D anyon in each pair to the single site and measure them to G. This is exactly this fusion tree in this quantum model. And the internal state X and Y are unknown. So this is preparable, and this is called a space VDDG. Okay, so they have shown that you have a universal logical gate set on this U model. They're composed by these 3 operations. The first one is braiding of D anyons. The second one are certain measurements, and the last one is a space transition. I will explain that one by one. The first one, braiding. Yes, as Nicholas said, how to do that remotely? We just have a pair of well-separated anyons, and then we move them, just exchange their position. So this is a braiding. You realize the first operation by our movement protocol easily, remotely. And then we move to the second one. What are those measurements in this universal gate set? They are anyon type measurements. This MU is the measurement into this U subspace and this U per subspace. This is nothing, but just we always want to come back to this computational space. So we want to do this measurement. But the key problem is here, how to preserve the coherence in this U space and this U per subspace. We must keep all the coherence in these spaces. This is very hard. Even Cui mentioned that in his paper, this is problematic. He does not know how to realize that. And we preserve the coherence and we realize it in our method. And the second one is called MA. We want to distinguish the total charge of the first 2 D anyon is A or not. In this U space, we only need to distinguish whether it is A or G. And if we are familiar with qubit computation, you will immediately see that this is the distinction between 0 space and 0 perp space. And this is a typical way to introduce extra computational power for a qubit. So by these 2 measurements, and by the braiding, and by the last one, they can realize the universal gate set. And we design a certain anyon interferometer to realize the measurement remotely. This is our contribution. So the logic is very simple. We want to measure this X anyon remotely. Then you will ask me, if we want to do the measurement, why don't we just move these 2 D anyon together to measure its total charge by doing fusion? But this is not good. Why? Because when you move them together, the distance between them is 0. Then any local error will cause a braiding. And this is a braiding gate happening on this logical state. This will give you a logical error. So we don't want this to happen. So we want to still keep these D anyons far away from each other, and then we still measure its total charge. This is our basic requirement to do that. And the procedure for this anyon interferometer is realized by these 4 steps. The first step, we create a pair of Z anyon and circle one of the Z anyon around this X anyon and come back to the original position. Then we do a measurement to fuse this Z anyon together. Note that in this case, those Z anyon are far away from this X anyon, so you don't need to worry about those errors in this X anyon. And we obtain a W anyon by fusing these 2 Z anyons. Then by a set of R move and F move calculation, you can resolve this Z loop and come back to a state with just a W anyon and 2 X anyon. Then you fuse this W anyon back with this X to come back to the original computational state. And the key thing is here, we have a phase factor in front of this state. this phase factor is just a phase and it is just a diagonal gate. In quantum mechanics, the measurements are always diagonal gates. So if you smartly choose this Z anyon to measure, you can finally design a specific measurement by this anyon interferometer protocol. So this is a basic logic. We try to design those phase I, X, E, W. The first measurement we want to realize is this MA. This MA is just projection into this A or not, right? And the realization is very simple. We have this fusion chip. We use Z anyon to braid around this first 2D anyon, obtain a W anyon, and fuse this W anyon with this D anyon, come back to the original fusion chip with a phase in front of that. And this phase, we smartly adjust that to get this diagonal gates. We choose Z equal D anyon, and then the measurement result, W, will immediately tell you what the AX anyon is. This is too detailed, but in our paper, like this X anyon is A, W anyon will definitely be A. And X anyon is G, W will be G. So we distinguish this A or G by reading this W anyon. So the first measurement is done. The second one, you want to measure that into this U and U per subspace, and the design is very similar. You also use a Z anyon to braid around the first 2D anyon, obtain a W anyon, and fuse it with G, with a G anyon. And when you choose Z equal to H, yeah, measurement result will only be A and B anyon, and they realize a probabilistic projection into the space U and U per. This means that if we want to repeat this for multiple times, the accuracy of this measurement to realize this MU measurement will be exponentially close to 1. So we also realize this second measurement in this method with accuracy arbitrarily high. So if you detailedly see any local errors in those measurement results, you will see that all local errors will only cause a global phase independent of X and Y, the logical states in this fusion chip. So this is potentially fault-tolerant, this measurement.
Quick question.
Yeah, please.
Yeah, sorry. Can you clarify for measurement to what you mean by using WG? Because at no point do you actually use it for B and bring them together.
So here in our anyon configuration picture, you have 4D anyon and 1G anyon, right? This
is just the fusion of the four. Basically.
No.
Oh.
Yeah, no. Because if you think about in the fusion chip picture, it's like you have a time direction. You can like do some like big rotation to this 2 dimension. So they have one-to-one correspondence between this fusion chip and this configuration in this 2-dimensional plane. So this fusion chip has 4D and 1G. In this 2-dimensional plane, it's 4D anyon, 1G anyon. They are well separated. And the internal information in this X and Y are unknown. And then if you want to do the braiding, for this 2D anyon is here. You create a pair of Z anyon, braid around them, and fuse that to W. This W will only be A and B, and then you fuse this, bring this W anyon with this G and fuse. Because they are Abelian anyon, so A fuse with G will be G, B fuse with G will be G. There is only one phase in front of all of those fusion chips. So that's the reason how can we design this measurement. And this is actually the key contribution in our paper. Yeah. So yeah, so we have realized the braiding of D anyons remotely, the measurement MA and MU remotely. The last operation is called fusion tree space transition. And this is important for realizing the multi-qubit gate. So what do I mean? I will explain that here. This is the qubit in the U model, right? You have this fusion tree. And then if we want to do multi-qubit gate, you need to fuse this 2 qubit into a larger fusion tree, like here. The 2G anyon is fused into another G anyon. You need to go into this fusion tree space to do the braiding of this D anyon. Then you can realize this CZ gate, multi-qubit gate. And then you also want to, after the computation, you come back without losing any logical information. So we also devise this protocol by combining movement and interferometer to realize the transition between these 2 fusion tree space, such that the fusion tree space transition is realizable and the multi-qubit gate is also realizable. So this is our contribution in this universal gate set. As a summary, this is a U model, have a qubit, and then the gate set is composed of these 3: braiding, measurement, and this transition between fusion tree space. We realize the first one by devising the protocol for moving anyon. And then we solve the second one by just devise this interferometer to do the remote measurement. And by combining the first two, we realize this fusion tree space transition to realize this multi-qubit gate. So this is our first contribution to realize this universal computation remotely, and it is potentially fault-tolerant. Then you will think about how can we realize this model in experiment. So we move to the second part. We construct a circuit for this quantum S3 on experiment to manipulate those anyons. So our computation is by this universal gate set. And the basic operation is just shortest ribbon operator with this measurement of this anyon type. We only want to realize these two. We can realize all those operations on this qubit and qutrit, whatever. Yeah, there are many circuit realizations before, as I mentioned. Like this is by Broby. They have shown that you can use that to manipulate anyons. This is a ribbon operator. This is exactly a ribbon operator for these anyons. So why don't we just use that in our protocol to realize this F operator? And it's not, but it is not true because when there is noise, you cannot directly generalize this to this noisy environment. There are several reasons. Let me explain that one by one. The first one, single site error in this circuit will propagate to a high density of error. Like because you have this entangling gate in this circuit, the error in the first qubit will propagate to this whole ribbon, as I explained before. So this will cause a logical error. You don't want this to happen. And the second problem is that the measurement operator, MK, has not been constructed in their paper and in these previous papers. So we construct this MK measurement operator, and then we also construct a way to use this shortest ribbon operator to move anyon and to do fusion and to do quantum error correction. So this is our first part. And the second part is for fusion. Actually, the fusion of non-Abelian anyon result is determined by this local degrees of freedom. And if you want to avoid the local degrees of freedom, this is unknown to avoid the problem. So how can you do that? We use this maximally mixed local degrees of freedom. We create a circuit to create an anyon with maximally mixed local degrees of freedom to avoid any subtlety from this local degrees of freedom. These are the two things we want to do. Yeah. So we construct a circuit to create a maximally mixed local degrees of freedom. And the logic is very simple. Like because S3 group can be decomposed into this semi-direct product with this Z2 group and Z3 group. So you can just write that into qubit and qutrit. So that is the basic logic. Each edge is a group element in S3 that can be encoded into a qutrit and qubit pair. And then you will ask me, because we have non-trivial algebra in this semi-direct product structure, how can we realize that? The semi-direct product structure is given by this conjugated, the generator of the Z3 group by this Z2 group will map it into the inverse of the Z3 group. This is a control flip of the qutrit by this qubit. So you have this control charge conjugation gate in this circuit. You can see the application of the control charge conjugation gate on this qutrit and qubit is just you flip the qutrit by this qubit, and it is done. All other gates are somehow trivial. Only this one is non-trivial. By detailing work out the algebras in the ribbon operator, take 2 months, yeah, and you will see how to construct these ribbon operators. We construct a circuit for all anyons A to H in this kind of S3. This is one example. This is F. This is shortest C ribbon operator. Yeah, and you will see there are 2 control charge conjugation gates in this ribbon operator, and you have some measurements and other things. To create a maximally mixed local degrees of freedom, we create some bell pair and we trace that up to introduce this maximally mixed local degrees of freedom. But this is too detailed. I will not go through that. By the similar logic, we also construct a circuit for this KRC operator. So we have done all of those circuits, and then these circuits are compatible with the manipulation of S3 anyon. So we have some realization way in this current experimental platform, like right bracket atom or n-chaps. And here, one important conclusion is that the only non-Clifford gate, if you still remember, non-Clifford is the gate that has magic, right? Magic state distillation. The only non-Clifford gate in this circuit is this CC gate. This means that it is very easy to control the error, and it is very important for this error control in this circuit game. I will introduce the way how do we suppress this error. And this is our third part, active error correction. We want to correct the circuit level noise. This is our goal. And then our basic operators are just this ribbon operator and this MK measurement. During the process, we do computation. There will be circuit level noise appearing as poly operators on this idling qubits and qubits in this quantum memory, and also on the circuit of this F operator. If we assume this measurement is perfect, this will always project those errors into some anyon errors in the anyon configuration picture, right? As an example, we can look at this one. If you have an X error, poly X on some edge, by this measurement, you will see a pair of D anyons at those two sides and a pair of C anyons at the other two sides. And in the middle side, C and D anyon, they fuse together to get a D anyon. So we can always read those errors in the circuit to those errors in these anyons. This is a basic logic. Then you will ask me, like, can we always like correct those anyon errors by fusion, correct those anyon error such that we correct those circuit level noise? This is a problem that we don't know. But the answer is yes. In our paper, we prove that if you want to correct the circuit level noise, you only need to map it into anyon errors by this MK, and then do this error correction in this anyon configuration picture. Because those anyon configuration, the anyon creation operator, they form a complete orthonormal basis in this two-dimensional plane. If you can do error correction in one complete orthonormal basis of operators, you can do the error correction in any circuit level noise with the sensor port. This is a theorem from Liyuan and Chen. Yeah. We proved that they have a complete orthonormal basis, such that the only thing, if you want to do error correction, is how to correct anyon errors. We want to find this algorithm to correct anyon error. If you can do that, our protocol is one protocol that can do fault-tolerant universal computation. But we have not found this one, but this will be our future direction. But there are many hints showing that this algorithm exists. Like in these studies, previously, they have shown that non-Abelian anyons, S3, you can do quantum error correction by Wuto. Yeah. Wuto is a very smart guy in this error correction part. Yeah. And then, but the assumption here is that anyons can be moved instantaneously. As I mentioned that we cannot do this. Non-Abelian anyons cannot be moved instantaneously. So you need to consider continuous error correction. And for continuous error correction, this is a dynamical process of creating and annihilating anyons. So you must suppress the error to very, very low, such that the density of anyons are very, very low, that you can always avoid the out of control of these anyons. This is the basic logic. Following this intuition, you can explain why Ising anyons has this 10 to the minus 17 threshold. You have to ensure that these errors below this threshold, such that you can correct the error. Otherwise, it will immediately propagate out of control. So if we expect that a similar thing happens for this quantum number S3, we have small but finite error threshold for quantum number S3. What should we do? How can we suppress the error below this 10 to the minus 17? This is our solution. We construct the error correcting code, qubit and qubit code, having all of those logical gates in this quantum number S3 circuit, and use them to do encoding for each physical qubit and qubit. This is called concatenation, a concatenation of topological code and its local code. By doing that, the local error rate will be suppressed to the logical error rate of this local code. Yeah, we can do error correction locally, and then the error rate will be suppressed to very low. And this will definitely give you the solution to satisfy this possible low threshold. So this is our contribution. We construct this qubit and qubit codes with a fault-tolerant logical CC gate. This is non-trivial because every code with a fault-tolerant logical non-Clifford gate is very rare. Like if you find that, you can find many things out of that. This is our contribution, and I will not go into the detail, but I will give you some hints about how to do that. To realize the fault-tolerant control charge condition gate, you select an odd integer n, and then the qubit code is a n square 1 n short code, and the qubit code is a n1d CSS code. If you just do that, and this gate will be in this form, it is very similar to a transversal construction, so the error will not propagate out of control. Yeah. So this is just some hint on how to construct that. So finally, by doing this encoding, the logical error rate of this code can be suppressed below this possible very small threshold, and we can ensure this works. So you can see everything are done. Only the remaining thing is how to find the algorithm to do continuous error correction in this quantum of S3. If this can be found, yeah, we can build a large scale quantum computer using this protocol. Yeah, so let's go to our summary. Yeah, in summary, like people want to build a universal quantum computer that is capable of doing quantum error correction, and it is experimentally feasible. And one of the potential choice is this topological quantum computation, right? And then we find that maybe S3 is the optimal solution of all of those topological orders. Then we build all of those protocols in our paper. For this universal gate set, we consider we use anyon interferometer to do remote measurements, and then we do the multi-qubit gate to realize this gate set remotely, and then we construct a circuit realization of all this protocol in qubit and qutrit. Then we consider how to do active error correction on the circuit level noise, such that we can always correct them by just moving anyons. An important thing is that the error threshold may be very, very low, so we do this encoding by our local code, and then we suppress the local error rate to extremely smooth. Yeah. So all our contribution combined together is a step toward a practical topological quantum computer. And in the future, what we can do? The first thing is definitely this continuous error correction algorithm. This is what we are doing. If you have this algorithm and you prove that you have a threshold in this S3 quantum double, this will finally give you this way to realize a universal quantum computation that is fault-tolerant. And also another thing is that, yeah, you can think about how to do constant depth protocol for all of this computation, because our computation is linear depth, so the depth is very, very, very large. But for torical and colorcal, their computation are realized in constant depth circuit, so their resource overhead is like relatively small compared to this linear depth protocol. And I think like here as an experts, maybe Leo, yeah, we can talk about this together about how to realize that in a constant depth protocol. Yeah, this will show that it can be better than this torical and colorcal. And the third one, you want to find a practical application of this protocol. For example, how to realize that in experiments like neutral atom or ion traps, and also how to think about some near-term algorithms. Namely, we only need shallow depths of circuit to do some computation that is classically hard, but quantum efficiently. And the last one, our local codes enables a fault-tolerant logical gate. So we can, the first thing is how to improve that to a better code, such that the resource overhead can be reduced. And also, we can develop some magic state dissolution protocol between qubit and qutrit, because this is something new. Previously, the magic state dissolution is on equal dimensional system. But right now, we have unequal dimensional system. We have a fault-tolerant non-Clifford gate between them. You can also think about how to develop such protocol to make the magic state dissolution better. Yeah. So if we can realize all of these things, our protocol is not just a step to a practical topological quantum computer, but just a protocol that can realize a large-scale quantum computer, and this will bring us into the future. Yeah. So this is what I prepared today. Thank you very much.
Thank you very much, Liyuan, for a really interesting talk. I'm sure there are many questions.
Yeah, please. Yeah, please.
Yes.
Yeah, so is the difficulty in constructing a
Liyuan, could you stop sharing your screen?
Yes, stop sharing.
is the
Yeah.
difficulty in constructing a error correction protocol for S3 in particular, because certain anyons can fuse to themselves, like there are like other anyon theories, like for example G4 topological order, where anyons don't fuse to themselves. And so I'm just wondering like what you anticipate the difficulty is for constructing anyon cleanup protocols for S3 and like other quantum doubles.
Yeah. So firstly, for this D4 anyon, they are called nilpotent anyons, right? And this is very similar to Ising anyons. Ising anyon, non-Abelian anyon will fuse to Abelian anyons, such that this is why it is easy to do error correction. But the problem is that very similar to Ising anyon, we do not have a universal gate set
Mhm.
for tolerantly in those models. It has not been proved for D4 anyon we have a universal gate set. So that maybe here you have one property like its error correction is easier, but the computation will be harder. So yeah, you cannot balance this. So that's the reason why people don't want to build some computer by these easy anyons. So you need to select the optimal point between those three properties.
There's no theorem, I guess. Is there a theorem that's been proved that gives you a trade-off between computational power and ability to error correct, or is that just your intuition?
Yeah, this is just intuition because it is very hard, but this is very interesting problem to prove like in the future. But right now this is an intuition. But yeah, but you can think about that. This is very intuitive. Like for Topological, it is easy to do error correction, but computational power is weak. And for Fibonacci anyon, computational power is very good, yeah, but error correction is very hard. Yeah, so typically you want to think of, okay, this is an intuition. Yeah, but it's very good, like you can have a proof for that.
So are there any other comments here? What about online? Are there any questions online? Well, if there's no other comment, I'd like to thank Liyuan again for a really interesting talk, and we'll look forward to the next chapter too.
Also thank Arthur for supporting me for such a long time because we start this project maybe last year's summer. It has been 1.5 years, and finally we come up with this paper. Yeah. Tomorrow. Hopefully. Yeah, but we are also coordinating this. Yeah.
What is that? Maybe you should mention this other paper.
Yeah. And Leo is here. Leo is another paper also having some universal gate set based on some circuit for this S3 anyon. Yeah, maybe you can also like look at his paper. They use a different encoding and then they discuss different problems in their paper.
Do you want to say something, Leo?
Sure. Essentially, yeah, we have a different encoding, logical encoding for the universal gate set, but it's also based on S3 quantum double model. And I think the focus of the two papers is also a bit different. I think your paper here is more on the focus on the fault tolerance aspects of like how to construct each gate. And we try to provide more like lattice level detail of like the Ripon operator of how to manipulate the anyons. So yeah, I think the two papers complement each other in a different focus and different ways of realizing universal gate set and S3 level. Yeah.
So the hope is to post them together.
Yes, we'll try to coordinate that.
Yeah. Actually, in our paper, like we try to avoid any difficulty from this local diffusion freedom such that we choose this maximally mixed local diffusion freedom. But I have discussed with Leo, maybe we can have better control of this local diffusion freedom such that we can have much more efficient result compared with this probabilistic algorithm to move those angles. Yeah, maybe. So it is always good to communicate with each other to collaborate.
Thank you very much. See you next week.